So, welcome back. So, now we would start talking about ensemble based algorithms. Mind you that we were doing supervised learning algorithms. So, ensemble based algorithm is another important category of supervised learning algorithms. So, when the decisions are important, the humans really rely on one opinion. That is very common, right? We ask a committee or a group of people, we take multiple, we ask from multiple people to get multiple answers or multiple thought processes, right? Like it can be a jury verdict, right? It can be a second opinion from the doctor, right? It can be hiring panels so that we get multiple answers or the multiple thought processes. So, that is what the ensemble algorithm exists for the same reasons, where we do not rely on the answers or a solution or a reasoning by a single model, where we get the answers from multiple models. So, we rely on multiple solutions and then we do something in order to get or reach to a solution which could be robust, which can be trustworthy. So, the core idea over here is that collective intelligence, right, beats the individual intelligence. It is very obvious. So, many weak models would lead to one strong decision. So, here the core idea is that we would take up many weak models. The individual model may not be good enough, but when we combine them, it can be a strong decision, it can lead to a strong solution. So, an ensemble does not try to create a super genius kind of model. It rather creates an agreement among imperfect models. That is the core idea. Okay. So, why a single model would fail? Obviously, one model, it may be biased, right? It can be unstable, it can be overconfident, for example. So, the decision tree may overfit, for example, linear models may be quite oversimplified, right? The KNN algorithm may overreact to a noise. So, the ensemble method would reduce the individual weaknesses, and that is the core idea behind the ensemble techniques. So, if we talk about the ensemble based algorithms, so there are two philosophies of the teamwork. One we call it as a bagging, where everyone works independently, right. Random forest is one of the key algorithms where this method would involve creating the multiple versions of a model using different subsets of the training data, right. On the other hand, the other thought process is the boosting method or boosting thought process, where everyone learns from the past failures. One of the algorithms which is quite famous is gradient boosting. So, boosting is in a way a sequential technique where each model tries to correct the previous errors or the errors which was made by the previous models, right. So, that is the core idea behind your boosting methods. Let us talk about the random forest, which is, I told you, a very popular algorithm under the category of bagging. So, random forest would create decision trees as the base models on randomly selected data samples, would get the prediction from each of the trees, right, and selects the best solution by means of voting, or it can be a majority voting scheme, right. So, the example is, suppose we have 3 doctors, right, and each doctor sees a different subset of cases, for example. Individually they may err, they may be wrong, right, but together they might be reliable, and when we put together the thoughts of the 3 doctors, it can be more beneficial to me, right, and that is what the random forest thinking is all about. So, random forest does what better? So, it reduces the overfitting, it handles the non-linearity part as well, and it makes stable predictions. And random forest succeeds not by intelligence, but by the diversity. That is the thought process. So, what is the key insight over here is the different mistakes cancels out. Yeah. So, when I would like to use random forest or a bagging as such. So, when you are dealing with messy data, the real world data, right. The real world data is really clean, everyone knows that. It usually has noise, outliers, you might have missing values, irregular patterns. So, what does random forest would fit in well over here is that each tree sees a different slice of the data first. Noise affects some trees, not at all, not all the trees would be affected by the noise, and the final decision is, or the final decision by all the trees would be averaged. It can be in terms of it could be either average, or it can be it can be the voting major voting thought process, right. Now, when we use random forest, when the features relationships are uncommon or complex, so often we do not know how the features would interact with each other. And why random forest would fit in well over here is because the trees naturally captures the if else interactions which we have learnt in the previous session. So, the forest would combine each such interactions views quite well, and that is why, and that is the reason why the random forest would fit well. So, another reason could be like when you need feature importances, I need which all features are important, because in real world situation there can be thousands of features for a given data or for a given problem to solve. So, taking all the features may not be important. So, I wanted to learn what are the important features, and I would like to build the model only on those important features. So, sometimes you do not just want a predictions, rather you want to know what matters, which all features actually matters, right. So, random forest can tell you which feature would influence the decision the most. That is what we talked about, that importance of the feature. Which feature are almost irrelevant. So, the practical use cases could be the feature selection, the domain understanding, and the model trust building as well, right. So, let us now talk about something called boosting, and we would specifically talk about an algorithm called gradient boosting to understand more into it. So, boosting, I told you, is like a teacher who focuses more on your weak students, right. So, good teacher does not reteach every time. Now, what you already know, so something which you know, it would not try to reteach and would not encourage you to mug up, right. So, the key focus on what is getting wrong. So, the teacher would always focus on where you are not learning, what is going wrong, right, and that is what exactly the gradient boosting does. It is based on the idea of combining the multiple weak learners, right, usually these are decision trees most of the cases, to create a strong prediction model. That is the overall thought process behind your gradient boosting. And why it has become so powerful, boosting? Because the features are, or features on hard cases are difficult to find out, right. It focuses on the hard cases, it builds the models sequentially, and extremely high accuracy is something which is something which gradient boosting or the boosting methods are more popular with. So, the boosting would convert the failure into learning variants. Some of the well known boosting algorithms are XGBoost, Light GBM, CatBoost. They are very popular, especially when the in competitive scenarios, or when the competition kind of scenarios takes place. So, when would you like to use a boosting? When the accuracy actually matters the most. Like I told you, in competitions, risk scoring, it can be credit modeling, it can be the ranking problems, right. So, when the mistakes are expensive, you would rather like to go with the boosting method, right. So, now let us also talk about some of the important concepts in machine learning which everyone must know. We will talk about something called bias and variance. So, if a model makes a mistake, there are only two possible reasons behind it. Either it is too simple to understand in reality, right, or it is trying too hard to understand everything, okay. And that is, we are talking about bias and variance concept. So, in simple terms, bias would occur when the algorithm has what? A limited flexibility. to learn and the true signals. So, mind you that we would always try to learn the true signals from the data, which would be beneficial for us. So, in our data we might have true signals that we would like to learn, as well as the noise signals which we would not like to learn, but we cannot help it. You would always find the noise and the true signals both in your data, right. So, bias is actually an error from the erroneous assumptions in the learning algorithm. Okay. It is the error from the erroneous assumptions. So, let us try say for example, high bias. So, high bias can cause an algorithm to miss the relevant relations between the features and the target outputs. We normally call it as an underfitting kind of concept. So, it does what? It makes the strong assumptions, right, about the features in the data. It ignores the complexity and it underfits the data ultimately, leading to something called underfitting. I will talk about underfitting and overfitting in the next part. So, variance on the other hand would happen when the model is too sensitive to the data. Okay. It learns the noises, it memorizes your training data, and ultimately it would overfit. In a very simple sense, if you train your data on a training data, for example, and obtain a very low score, upon changing the data and then the training the same previous model, you experience a high error. So, this is a sign of a variance, right. So, if a model performs badly, so there are only two reasons. One is either it did not learn enough or it learned too much, and that is the underfitting and overfitting that I was talking about. So, underfitting happens when the model is too simple for the problem, right. So, underfitting would do what? It would miss the patterns most of the cases, it would ignore the importance of signals, it might perform badly everywhere, right. So, bad on training data and bad on the test data, right. On the other hand, overfitting happens when the model learns too specifically. Okay. So, overfitting would memorize your noise, it would learn irrelevant details, it would become fragile. It is excellent on training data, but it is terrible on new data. So, a student memorizes your previous year question papers, for example, right, and when he appears for the exams, if the question comes and he is able to recall it, good enough, otherwise he is not able to answer it well. So, result could be scoring 100% in mock test, for example, but he panics in the final exams with the question is a different one or the question has changed, for example, right. Let us also talk about a concept called train validation and test, as well as the cross validation concepts, right. So, here the train validation is means what? The test exists to keep the machine learning honest. Yeah. So, if a test during a test, if I test a student using the same question that I have taught him, and I am also testing him on the same set of questions. So, obviously, in a way it is memorizing, right. So, the same problem happens in ML also, right. So, if we train and test on the same piece of the data, we measures the memorization rather learning, not learning, right. So, think of the ML like preparing for an exam, right. The training set over on the other hand, or the training set actually means what? Learning phase, when you are trying to learn. So, the examples that you have been given, right. So, there is what the model studies, on the basis of which the model is being built up, right. So, it learns the patterns. So, during training it would do what? It would try to learn the pattern, or would try to see how the input maps with the output. It adjusts the parameters in this process during the learning. It would make the mistakes, right, would be able to make these mistakes freely, in fact, right, and there is no judgment over here. So, it is trying to learn in this particular phase. When it comes to validation set, you can think about as a practice set or practice exams. So, this is where we check if the learning strategy is working or not, right. So, I mean it can be used to tune the parameters specifically in this phase, decide the model complexity, compare the algorithms, So, in this phase the model I would say is still learning, but we are careful about it, right. When it comes to test set, that is the final exams, it can be thought of as a final exam. So, the test set must be touched only once, because obviously I would like to see how exactly my model has performed in the real world. So, test case or the test set is what when I am trying to see how my model actually would perform. So, it represents the unseen reality. Unseen means the data portion which was not the part of the training or neither the part of the validation part, right. So, it measures the true generalization that I would like to see whether my model has learned or not, right. So, the test set I would say should be kept as very sacred kind of data, right. It cannot be used during your training and during the validation phases, right. So, what goes wrong without a split, for example, right. If I do not split my data, so what goes wrong? So, ideally you understand one thing, like when you do a splitting of a data, so there are common thought processes. You normally like to have a major chunk of your data for the training part and some portion for the testing part and the validation part. So, normally we go for at least 60 to 70%, it depends, right, even 80% for the testing part, because for the training part where I would like to build the model, right. That is where it would try to understand how the model would try to understand how to learn those patterns, and then followed by maybe 10% for training validation part and 10% for the validation part. It can vary, right. So, what goes wrong I told you without a split. So, without a proper splitting, the models logs brilliantly, definitely, and it fails in production. So, when it builds up, okay, because you have used the entire set of the data, all the samples have been used for building the model. So, definitely it would build up a model, it might look good, right, during the training phase. But when it comes to production, when it comes to apply this model on the real world scenarios, it might fail. For example, 99% accuracy in lab and 60% accuracy in the real world. So, this is something which is not desirable, right. So, it could be the reason, could be the overfitting, it could be the data leakage, it could be the biased evaluation, right. So, that is it for today's session, and in the next session we would talk about unsupervised learning algorithms. Thank you.